I want you to imagine something for just a second. Think about your absolute favorite digital ecosystem.
Okay, yeah.
The game you have poured, I mean, just hundreds of hours into. And probably a pretty significant amount of capital, right?
Oh, absolutely. We all have one.
Right. So picture the inventory you've built up over all that time.
The loot.
Exactly. The loot. Maybe it's a high-tier loadout or a meticulously crafted character build, or maybe just an exclusive digital asset you managed to acquire.
Like a rare skin or something.
Yeah, exactly. And when you log in and look at that inventory, the psychology of it is incredibly convincing. I mean, it really feels like yours.
It does. It's designed to feel that way.
But then you wake up to an announcement. The studio behind the game has maybe lost its publishing rights.
Which happens more often than people think.
Right. We saw this happen dramatically with games like Marvel Heroes, or even, structural wipes like the transition to Overwatch 2.
Oh yeah, that was a huge deal.
So the servers are slated for shutdown. And just like that, the digital real estate you thought you owned just entirely evaporates.
Poof. Gone.
Gone. Because you didn't actually own any of it, did you? You were just basically a tenant in a digital fiefdom.
That's a great way to put it. It is a really jarring realization for most users.
Yeah.
Primarily because the UX, the user experience of modern applications, completely obfuscates the legal and structural reality of what's actually happening.
Which is what we're going to get into.
Oh.
Welcome to this deep dive, everyone. Our mission today is to tear down that exact structural vulnerability.
Yes.
We're going to examine the architecture of a decentralized application, a DApp built on the EOS network.
And it's a fascinating one.
It is. And on the surface, the application we are looking at is almost comically simple. It's literally just a game of Hangman.
Right. Guessing a word.
Yeah. But do not let the front end of a word-guessing game fool you.
Okay, let's unpack this. Because we're using this seemingly simple contract to analyze a massive, seismic paradigm shift. A total shift in how we handle cryptography and data ownership.
Exactly. And zero-knowledge architecture. We are basically looking at the blueprint for completely trustless digital systems here.
Yeah, the Hangman contract serves as a perfect microscopic model for all of this.
Right.
The game itself is totally irrelevant. It's the underlying engine we're dissecting today.
Because if you could do it with Hangman.
Exactly. By looking at how something as trivial as a hidden word is managed securely on a public ledger, we can extrapolate how incredibly complex legal, financial, and entertainment systems will be structured in the near future.
It's wild to think about. But to really grasp the gravity of building even a simple game on a decentralized network, we basically have to contrast it with the standard licensing model.
The one that completely dominates the software industry right now.
Right. We are looking at a transition from what we call digital serfdom to true cryptographic ownership.
Which is a huge leap.
It is. If you're listening right now and you've ever dealt with an end-user license agreement, which, let's be honest, literally none of us read.
Nobody reads the ELA.
Right. You just scroll to the bottom and click accept. Well, you've unknowingly agreed to this serfdom.
You have. The ELA is basically the legal manifestation of centralized architecture.
How so? Break that down for us.
Well, because the game logic, the physics engine, the user data, all of that lives on a monolithic server stack.
Like AWS or Azure.
Exactly. And it's controlled entirely by the publisher. So the legal framework, the EULA, has to protect their absolute authority over that server stack.
Right, so they can pull the plug whenever they want.
Precisely. In those centralized systems, you're participating in a revocable trust. You are literally just paying for a localized license to temporarily modify a row in their proprietary database.
I just want to pause there because that phrasing is so important. A localized license to modify a row in a database.
Yeah, that's all buying a sword in a game is.
Wait, but I want to push back playfully here for a second. If I buy a legendary skin in a traditional game, I feel like I own it. It's sitting right there in my inventory.
It feels like ownership, sure.
Yeah, I paid $20 for it.
Right, but think of it like renting an apartment versus owning a house.
Okay, I like that analogy.
When you rent an apartment, you can decorate it, right?
Sure.
You can hang up pictures, put in a nice rug.
Make it feel like mine.
Exactly. But at the end of the day, the landlord can still evict you. Or they can literally just change the locks while you're at work.
Because they own the building.
Because they own the building.
Yeah.
True asset ownership flips both the legal and structural architecture upside down.
So how does a blockchain fix the landlord problem?
Well, in a decentralized environment, assets are minted as cryptographic tokens or NFTs.
Right.
And the critical distinction here isn't just that it's on a blockchain, it's that the asset is bound mathematically to a private key that only you, the user, hold.
Right, which means the publisher completely loses the master key to the building.
Exactly. I think people often conflate.
They can't force you to use their auction house.
Exactly.
I want to push on that, though, because the ownership aspect is massive, but it's really just one part of the equation here.
True.
We also have to talk about immutability and transparency, because this fundamentally solves the black box problem of modern software.
Oh, the black box problem is huge in gaming right now.
Right. I mean, if you play competitive games, you have definitely experienced the frustration of nerfing.
Yep. Everyone hates a nerf.
You spend months, maybe years, acquiring a top-tier asset or character.
Yeah.
And then the developer silently pushes an update.
Usually in the middle of the night.
Yeah. And it completely alters the asset's underlying variables. The drop rates change, the performance degrades, and there's absolutely no auditable trail. You just log in and your character is suddenly terrible.
Right. And that black box exists because the code base is proprietary and hidden on their servers.
Right.
But on a decentralized network, the core game logic is deployed as a smart contract.
Which means it's public.
Exactly. That code is compiled, deployed to the ledger, and it becomes permanently visible and immutable. Unchangeable. If a contract dictates that a specific reward has an algorithmic drop rate of exactly 0.5%, that variable is hard-coded.
Yeah.
So anyone, literally anyone, can query the blockchain state and mathematically verify that drop rate.
So it basically forces developers into absolute honesty.
It really does.
If they want to change the mechanics, they can't just hotfix a database at 3 a.m.
Yeah.
They have to deploy a completely new version of the contract, right?
Yes. Or they have to route the proposed changes through a decentralized governance protocol.
Meaning the players actually get a say.
Exactly. Where stakeholders actually vote on the parameter updates, the code becomes the ultimate neutral arbiter.
That neutrality is just, it's so key. And it acts as the foundation for interoperability, right?
Yes, the holy grail of digital ecosystems.
Right. We always hear about the holy grail of gaming.
Yeah.
Let's run a hypothetical scenario to make this really concrete for the listener.
Sure.
So say I earn a highly specific, cryptographically verified asset in a sci-fi RPG.
Okay, you've got your sci-fi asset.
Right. Because that asset's metadata and the proof of ownership live on the public ledger. A completely unrelated developer, someone building, say, a racing simulator, could use it.
Right, they could program their own smart contract to query the ledger.
Exactly. Their contract could basically say, if the user connecting to our racing game holds the sci-fi RPG asset, automatically unlock a custom vehicle chassis for them.
That is the exact mechanism. And the beauty of it is the developers of those two applications do not need a corporate partnership.
They don't even need to talk to each other.
Exactly. They don't need to share API keys or sit down with lawyers to negotiate data sharing agreements.
Right.
They are both simply reading from and writing to the exact same open state machine.
It totally dissolves those walled gardens that currently define the entire tech industry.
It really does. And as long as the underlying network consensus is maintained by the distributed nodes, the assets and their interoperable potential exist in perpetuity.
Forever, which naturally cultivates this incredibly robust, integrated token economy.
Absolutely.
When scarcity is actually enforced by cryptographic math, rather than just a corporate promise that they won't print more items, these assets acquire genuine economic weight.
They become real financial instruments.
Right. But okay, this brings us to a massive, unavoidable bottleneck.
I know where you're going with this.
I mean, we have to address it. If we're talking about an architecture that provides verifiable ownership, absolute transparency, infinite interoperability, why aren't all games built this way right now? Why is the vast majority of the industry still relying on centralized server clusters?
It's a fair question, and the friction points are entirely infrastructural.
Meaning the blockchains themselves were the problem.
Precisely. The first generation of distributed ledgers, your early blockchains, they were engineered for asynchronous, low-frequency financial settlements.
Like sending Bitcoin to someone.
Right. They were absolutely not built for the high-throughput, low-latency demands of interactive software.
Let's use an analogy here, because I think our listeners generally know what gas fees and network congestion look like on older proof-of-work networks.
Oh, yeah. It can be painful.
Yeah. Imagine playing a fast-paced game, like Super Mario.
Okay.
But every single time you press the jump button, you have to wait 10 seconds. And not only that, you have to pay a $5 toll to a guy in a booth just to process the jump.
Right. Traditional blockchain gas fees.
Exactly. It completely ruins the game. If every single microaction in an application requires a network fee and a 12-second block confirmation, any interactive experience is just dead on arrival.
It's unplayable. But what's fascinating here is how the specific implementation we are analyzing today solves this. The Hangman DApp leverages the EOS network precisely because it fundamentally restructures resource allocation to circumvent those exact bottlenecks.
Okay, so how does EOS actually bypass the toll booth guy?
Well, the EOS architecture utilizes a delegated proof of stake, or DPoS consensus mechanism.
Yeah.
Instead of the probabilistic consensus models that cause all that high latency on older chains, DPoS relies on a deterministic schedule of block producers.
What does that actually mean for the speed?
It means the network can achieve confirmation times of roughly 0.5 seconds.
Wow. Half a second.
Yes, and it can process upwards of 3,000 transactions per second natively.
That half-second latency is really the magic number, isn't it?
It absolutely is.
Because from a user experience perspective, half a second is the threshold where a distributed network starts to just feel like a localized server.
Exactly. The delay is negligible.
Right. If you click a button to guess a letter in our Hangman DApp, you need the front end to reflect that state change almost instantaneously.
If the user has to wait for a probabilistic block confirmation like 10 or 15 seconds, you've completely ruined the flow state of the game.
Nobody is going to play a Hangman game that takes a minute per letter.
No one. Furthermore, the fee structure is entirely inverted on EOS.
Okay, break that down.
On legacy networks, the user pays a fluctuating gas fee for every single state change they push to the ledger. Every click costs money.
Right.
But EOS utilizes a resource staking model. It involves three things: CPU, network bandwidth, which they call net, and RAM.
Okay.
And here is the kicker. The developers of the decentralized application can stake the necessary CPU and net resources on behalf of their users.
Wait, on behalf of them. So the developer pays the toll.
Essentially, yes, which means the end user experiences zero gas fees.
Zero. Wow. That is a massive paradigm shift.
It changes everything.
It really does. It means we can actually execute microtransactions. And I don't mean that in the financial sense of spending $1 in a cash shop. I mean it in the computational sense.
Right, recording a highly granular action on-chain.
Exactly. Every single letter guessed in this Hangman game is a discrete transaction pushed to the public ledger. If that costs even a fraction of a cent per guess, the economic model would totally collapse.
Nobody would play it. And we also must factor in the ecological footprint, which is a major point of friction for mainstream adoption of decentralized networks right now.
Oh, for sure. The environmental angle is always brought up.
And rightfully so. But because the DPoS model relies on a highly optimized, multi-threaded consensus process among a specific set of active block producers.
It doesn't need all those massive mining farms.
Exactly. It doesn't require the massive computational hashing races that define legacy proof-of-work systems. We are talking about energy consumption in the realm of 0.00001 kilowatt hours per transaction.
0.00001. That is incredibly tiny.
It's minuscule.
To contextualize that for you listening, that efficiency metric makes interacting with this ledger fundamentally less energy intensive than a standard query to a traditional centralized cloud server.
It scales sustainably. It's cleaner than Web 2.
So we have the rails built now. We've got high throughput, sub-second latency, zero end user fees, and a negligible energy footprint.
The perfect foundation.
Exactly. So now I want to look at how a developer actually maps a piece of interactive software onto this infrastructure. Let's dissect the anatomy of the Hangman DApp that's currently deployed on the Jungle 4 testnet.
Yeah, the Jungle 4 environment is fantastic. It allows developers to basically stress test this Hangmantis 1 smart contract under real network conditions, but without consuming costly mainnet RAM.
Right, so it's a sandbox.
A very realistic sandbox.
Yeah.
And to really understand the application, we have to look at how state is structured on an EOS-EO chain.
Okay.
Because unlike traditional relational databases like SQL, state here is stored in highly optimized in-memory tables.
And reading the schema of these tables is fascinating, honestly, because it forces a complete mental reset for a traditional Web 2 developer.
That's completely. It's a totally different paradigm.
Normally, your database schema is heavily guarded, right? It's behind firewalls and complex application layers. But here, the structure is just completely exposed on the blockchain.
Anybody can look at it.
Yeah. So the contract defines two primary tables. We have the titles table and the games table. Let's break those down.
Sure. The titles table basically acts as the master directory. It utilizes a primary 64-bit integer key, which is the id.
So like ID number 1, 2, 3, etc.
Exactly. Then it stores the visual pattern, This is the string of dashes that the front end uses to render the blanks for the user on the screen.
But the movie is Jaws. The pattern is just 4 dashes.
Exactly. And crucially, it stores a hash, which we will definitely analyze heavily in a moment.
We will. And then we have the second table, the games table. This one handles the active session state, right?
Right. So if you initiate a session to play, a row is either created or updated for your specific account name.
Right.
It tracks the title you are currently trying to solve. It has an attempts counter that decrements from 5 down to 0 as you make wrong guesses.
Classic Hangman rules.
Yep. It also has an integer-based status flag indicating whether the session is active, won, or lost. And finally, a last guess field.
Okay, so that's where the data lives. And the state machine itself is driven by 3 primary executable actions, right?
Yes. Start game, guess word, and end game.
Let's walk through those. When the user triggers start game.
The contract pseudo-randomly selects an id from the titles table. It initializes the user's row in the games table with those 5 attempts and sets the status to active.
Right. And here's where it gets really interesting. Because this architecture creates an incredibly strange paradox.
It really does.
If you are listening to this, I want you to think about the fundamental mechanics of a guessing game. The entire premise relies on information asymmetry.
Right, the user must not know the answer.
Exactly. But we just established that the blockchain is a completely public, transparent, immutable ledger. Every single node globally has a copy of these exact tables we just described.
Yep, the RAM state is completely open.
Any user could theoretically pull up a block explorer, query the RPC endpoint of an EOS node, and read the raw state of the titles table.
Which means the transparency of the medium seems fundamentally incompatible with the requirement of hidden information.
Exactly. If the game simply stored the string, let's say the matrix, in the titles table, a user could bypass the front end, look up their active title in the Explorer, and just read the plain text answer.
They'd win every time.
Yeah. The game would be structurally compromised by the very nature of the blockchain. It makes no sense at first glance.
Which brings us to the cryptographic core of this entire application, and honestly, the core of modern Web3.
Right.
If you build on a public ledger, you cannot hide data. You can only obfuscate it mathematically.
That's a great rule of thumb.
And this is why the plain text of the Netflix movie titles is never pushed to the network. It literally never touches the blockchain.
So what's in the table instead?
The contract utilizes a cryptographic hashing function, specifically SHA-256.
Okay, let's dive deep into the mechanics of SHA-256, because this is genuinely the linchpin of modern cryptography.
It is the workhorse of the internet.
Yeah. So SHA stands for Secure Hash Algorithm. It takes an input of literally any size, it could be a single word or an entire set of encyclopedias, and processes it through a deterministic algorithm.
Right, and it always produces a fixed-length string of 64 hexadecimal characters.
Always 64 characters. And the critical properties here are collision resistance and pre-image resistance.
Yes.
Explain pre-image resistance, because that's the one-way street, right?
Exactly. Pre-image resistance means that it is a mathematically one-way function. If I give you that 64-character hash, it is computationally infeasible for you to reverse engineer the algorithm to discover the original input.
So even with a supercomputer, you're not unhashing it to find out it says the matrix.
Right. It would take longer than the lifespan of the universe to brute force it.
It's essentially a digital fingerprint.
That's the perfect analogy.
Think about a bouncer guarding access to a highly secure VIP club. The traditional Web 2 model has the bouncer holding a ledger with everyone's plaintext names on it.
Right.
But if that ledger is compromised, if someone steals it, everyone's identity is leaked. The zero-knowledge approach replaces the names with fingerprints.
The bouncer doesn't actually know who John Smith is.
Exactly. When you arrive, you don't say your name. You just press your thumb to a scanner. The bouncer compares it against the list of approved prints. If there's an exact mathematical match, access is granted.
The system validates the truth of your identity without ever actually knowing it.
It's brilliant. And that maps perfectly to the guessword action in our Hangman smart contract.
It does. Let's trace the exact execution path when a user submits a guess.
Okay, walk us through it.
So the user types a movie title into the front end, let's say they guess Inception, and they sign the transaction in their wallet.
Step 1. The smart contract normalizes the input. It forces the string to lowercase.
Right, because you have to prevent capitalization mismatches from failing a technically correct guess. Inception, with a capital I and a lowercase I would produce entirely different hashes.
Completely different fingerprints.
Okay.
So step 2 is where the cryptographic magic actually happens.
Yes. The EOS smart contract takes that normalized lowercase input and executes the SHA-256 algorithm locally within the WebAssembly virtual machine that's processing the block.
So it generates a hash of the user's guess on the fly.
Exactly, right there in the moment.
And then step 3, it compares the dynamically generated hash of their guess against the static hash permanently stored in the titles table for that specific title.
And step 4 is the state resolution. If those two hashes match perfectly.
The browser lets them in.
Exactly. The contract mathematically proves the user knows the secret word without the contract ever having stored the secret word itself.
That's so cool.
It really is. So it updates the game's table status to 1, which means a win. But if they do not match, the attempt's counter decrements.
It's just incredibly elegant implementation of zero-knowledge architecture. I mean, the secret is completely secure, yet the verification process is entirely transparent and mathematically guaranteed for anyone to audit.
It solves the paradox perfectly.
It does. But, you know, as brilliant as this back-end logic is, a major barrier in Web3 has always been the front-end friction.
Oh, the UX has historically been awful.
Right. If you are a standard user, you do not know how to construct an EOCO serialized transaction payload. You don't want to know about hashes or WebAssembly.
You just don't want to play Hangman.
Exactly. You just want to play the game.
The user experience must abstract all of this cryptographic complexity away. And that is where the integration of modern SDKs comes in. Specifically, tools like WharfKit.
Let's break down WharfKit because the source material brings this up as a key component.
WharfKit is what bridges the deterministic virtual machine of the blockchain with standard Web2 browser environments.
Because historically, developing a front end for an EOS dApp required managing really complex RPC calls, right?
Yes, and handling ABI application binary interface translations manually. You were basically wrestling with wallet connections constantly.
Sounds like a nightmare for a front-end dev.
It was. But WharfKit standardizes all of this. It provides a clean API surface so a web developer can interact with the smart contract using familiar JavaScript or TypeScript paradigms.
So they don't have to learn a completely new decentralized language just to build a button.
Exactly. WharfKit essentially acts as a highly optimized translation layer. It takes the button, click on the React or Vue front end, structures it into a proper EOCO transaction format, and then routes it to the user's wallet for signature.
And the wallet integration itself is crucial here, particularly the use of Anchor Wallet for session management.
Because the last thing we want in a rapid-fire guessing game is for the user to face a cryptographic signing prompt every single time they type a letter.
Imagine a pop-up interrupting you for every single letter you guess in Hangman.
The UX would be absolutely abysmal.
Yeah. So how does Anchor solve that?
Anchor solves this via background signature caching and local permissions. When the user first connects to the Hangman dApp, they establish an authenticated session. They essentially grant the front-end localized permission to sign specific actions like the guessword action on their behalf.
Oh, so they pre-approve it.
Exactly. Without requiring manual approval for every single execution going forward.
It mirrors the seamlessness of traditional session cookies on regular websites, but it's backed by cryptographic keys.
It's Web 2 convenience with Web 3 security.
I love that. Now, I also want to examine the sheer scale of the data management here, because the architecture involves seeding approximately 8,800 Netflix titles into the smart contract's RAM.
Which is a significant logistical hurdle.
Right, because RAM isn't free.
No, on the EOS network, RAM is a finite market-priced resource. Storing data permanently in state costs money.
And beyond the financial cost, there's the computational overhead, right? Pushing 8,800 individual transactions to populate that titles table.
Exactly. If a developer tried to seed that data sequentially, like one transaction at a time for all 8,800 titles, it would be wildly inefficient, both in terms of network bandwidth and just raw developer time.
So how do they get around that?
This is where the maturity of the EOCO contract development toolkit, the CDT, comes into play, specifically versions 3.x and 4.x.
Okay, what do they offer?
The smart contract utilizes an add bulk action. It allows the developer to batch process arrays of titles in a single transaction payload.
So you pass an array containing hundreds of pre-calculated hashes and visual patterns all at once.
Yes. And the WebAssembly environment iterates through them, inserting them into the titles table in one sweeping motion.
That is so much cleaner. It really showcases that the infrastructure is built for enterprise-scale data seeding, not just localized testing.
Exactly. The tooling has evolved to the point where the friction of interacting with the blockchain is almost entirely mitigated for both the developer and the end user.
It sounds utopian.
Almost too good to be true, right?
Right. And as you'll note, every system has its vulnerabilities. However, we have to critically analyze the implementation. While the infrastructure is robust, the specific logic of this Hangman 1 contract contains architectural vulnerabilities that would be fatal in a high-stakes environment.
They absolutely would be.
And this brings us to the catch. If we were evaluating this as a blueprint for future trustless systems, we have to stress test it.
We have to try to break it.
Exactly. The source documentation explicitly lists 3 major limitations, and I want to dive straight into the first one, the pattern matching vulnerability. Because as I was reviewing the contract logic, this immediately stood out to me as a critical side-channel attack vector.
It's a glaring flaw. Let's unpack the mechanics of that vulnerability.
So we established that the SHA-256 hash is mathematically unbreakable. A bad actor cannot derive the plain text from the hash.
Right. The cryptography holds up.
However, the titles table also stores the visual pattern, right? The exact sequence of characters and spaces.
The dash.
Right, the dashes. Furthermore, the parameters of the game are public knowledge. We all know the dataset is exclusively comprised of Netflix movie titles.
Which creates a finite, highly structured data pool.
Exactly. If the smart contract serves my front end a pattern that is exactly 7 characters, a space, and 3 characters, I don't need to break the cryptography.
You don't need to touch the hash at all.
No. I can just write a really basic Python script to scrape a public database of Netflix titles, filter by that exact string length and space placement, and instantly reduce my possibilities from 8,800 down to maybe 3 or 4 titles.
You have entirely bypassed the cryptographic security by simply analyzing the metadata.
It's a huge loophole.
You've basically executed a perfect side-channel attack. You haven't attacked the vault itself. You've just looked at the size of the box being carried into the vault and logically deduced what must be inside.
Right. Now, in a purely recreational testnet environment like this Hangman game, this metadata leakage is mostly acceptable. Who cares if someone cheats at testnet Hangman?
Sure, but consider a scenario where this exact contract architecture was managing a high-stakes decentralized finance protocol, or a massive multiplayer economy with real monetary value attached to guessing correctly.
Bots would drain the contract liquidity in seconds.
Unquestionably. To secure this for a production environment, the architecture would need to obscure the pattern length entirely.
How would you do that?
Perhaps revealing it only after a certain threshold of cryptographic proofs were submitted, or by expanding the dataset dynamically so it cannot be easily pre-indexed by malicious scripts.
It highlights a crucial lesson for Web3 developers. Impenetrable cryptography does not matter if your application logic leaks the context.
Context is everything.
Okay, so that's the first limitation. The second limitation involves state management. The contract enforces a strict 1 active game limit per account.
Which is fundamentally an economic and resource management constraint. We discussed earlier how EOS utilizes RAM for state storage.
Right.
Every single row in the games table consumes physical memory on the block producer servers.
So if a user could spam the start game action and open 10,000 simultaneous sessions without ever resolving them, they would massively bloat the RAM state.
They would essentially be launching a resource exhaustion attack on the contract.
Forcing the developers to constantly purchase more RAM out of pocket just to keep the dApp functional.
Precisely. By requiring the user to explicitly call the endgame action to clear their previous row before initializing a new one, the contract maintains strict control over its state footprint.
It's a necessary garbage collection mechanism for decentralized architecture.
It is. You have to keep the state clean.
But the third limitation is the most complex from a computer science perspective. The documentation notes the reliance on pseudo-random title selection.
Ah, yes, the randomness problem.
Using a combination of tapoguess and time-based variables. Let's spend some time here because the concept of randomness on a blockchain is notoriously difficult.
It is one of the hardest problems in blockchain development.
Right. Because if I ask my local computer to generate a random number, it does it instantly. Why is a network capable of 3,000 transactions a second fundamentally terrible at picking a random number?
Because a blockchain, by definition, is a deterministic state machine.
Okay, unpack deterministic.
For thousands of globally distributed nodes to maintain consensus, they must all process the exact same inputs and arrive at the exact same outputs every single time.
So if the smart contract just says pick a random number between 1 and 10,
Node A in Tokyo might evaluate the function and pick 4, but Node B in London evaluates the exact same function and picks 7.
and the moment they arrive at different state outputs, consensus fails.
Exactly. The cryptographic hashes of the block do not match, and the network forks. True randomness is simply incompatible with deterministic verification.
Therefore, developers are forced to simulate randomness using data that is available within the block execution environment itself.
Right. And that is where TEPOS comes in, transactions as proof of stake.
How does TAPOS simulate randomness?
TEPOS essentially pulls data from recent block headers, which are generally unpredictable until the actual moment the block is produced, and combines it with the exact microsecond timestamp of the transaction execution to generate a pseudo-random seed.
It works for a testnet game of Hangman. It's random enough for that.
Yes. But the vulnerability here is that the block producer, the actual node compiling the block at that specific microsecond, has a tiny window where they know the variables before the block is finalized.
Oh, wow. So if the incentive is high enough, a malicious block producer could theoretically manipulate the transaction ordering.
Yes. Or slightly alter the timestamp to force the pseudo-random algorithm to output a specific desired result.
They could game the system from the inside.
They absolutely could, which means we need a way to inject true, verifiable unpredictability into a closed, deterministic system.
And this is where the solutions proposed in the documentation, VRF oracles and commit reveal schemes, become really critical for future-proofing these systems.
Yes, these are the industry standards for high-stakes randomness.
Let's analyze the VRF oracle first. Explain what that is.
VRF stands for Verifiable Random Function. An oracle acts as a secure cryptographic bridge between the isolated blockchain and external real-world data sources.
Okay.
Instead of the smart contract trying to generate randomness internally, it basically sends out a request for a random number from the external VRF oracle.
But wait, if we just trust an external server to give us a random number, haven't we just reintroduced centralized trust into the system?
That's a very common critique.
I mean, we are back to trusting a black box, aren't we?
We would be, except the oracle doesn't just return a number. It returns the random number accompanied by a cryptographic proof. The external hardware generates the number using real off-chain entropy, like measuring thermal noise in a CPU or atmospheric data, and then uses its private key to generate a mathematical proof of how that specific number was derived.
So when the oracle pushes the number back onto the EOS blockchain, the smart contract first runs that cryptographic proof through a verification algorithm.
Exactly. It mathematically guarantees that the external entity did not tamper with the generation process.
It's like rolling dice inside a sealed, transparent vault. We can't reach in and touch the dice ourselves, but we can verify with absolute certainty that they weren't loaded.
That's exactly it. Now, the other mechanism mentioned, the commit reveal scheme, achieves a similar result but through multi-party game theory rather than external hardware.
Walk us through how a commit reveal sequence actually operates.
It happens in two distinct phases. In the commit phase, multiple participants generate a random string of data locally on their own machines.
Okay.
They hash that data using our friend SHA-256 and submit only the hash to the smart contract.
So the contract is basically holding a collection of locked boxes, and no participant knows what the others have inside their specific boxes.
Precisely. Once all the hashes are securely locked in, the reveal phase begins.
And what happens then?
Every participant submits their original plain text data. The contract verifies that the plain text perfectly matches the previously submitted hashes.
Making sure nobody swapped their data at the last second.
Right. Once verified, the contract concatenates all the individual strings together, basically squishing them all into one long word, and hashes that combined result to create the final random seed.
That is brilliant. Because as long as even one single participant in the entire pool is honest and submits truly unpredictable data, the final concatenated outcome cannot be predicted or controlled by anyone else.
Not even the block producers.
Both VRF oracles and commit reveal schemes really represent the bleeding edge of solving the deterministic limitations of distributed ledgers.
They are the final puzzle pieces required to build high-stakes, fully trustless applications.
So when you step back and look at the aggregate of everything we've unpacked today, it really puts the sheer scope of this technological shift into perspective.
It's massive.
We started by discussing the frustration of losing a digital item on a closed server.
Right.
And we've traced the solution through high-throughput DPoS consensus models that eliminate gas fees. We analyzed the complex in-memory state management of smart contracts. And we explored the mathematical elegance of one-way cryptographic hashing to secure hidden data.
All working together.
We are looking at a system where a developer can build an environment, define the rules in immutable code, and then completely relinquish the ability to cheat or alter those rules.
It proves that we do not have to sacrifice user experience to achieve decentralization. That's the biggest takeaway.
Right. We can have applications that respond in sub-seconds, cost absolutely nothing for the end user to interact with, and are built on profoundly transparent, auditable foundations.
The Hangman app is really just a proof of concept. It's a sandbox for testing these cryptographic primitives.
And that leads me to the core implication I want to leave you with today. If you were listening to this, I really want you to project this architecture forward.
Look past the game.
Exactly. If developers can successfully utilize this stack, zero-fee execution, immutable state storage, and zero-knowledge cryptographic proofs to perfectly secure a trivial game of Hangman on a public ledger, what happens when we apply this exact same framework to the structural pillars of our society?
The applications for verifiable truth without data exposure are virtually limitless.
Consider the architecture of modern healthcare data. Right now, your most sensitive medical history sits in siloed, highly vulnerable centralized servers.
Which get hacked all the time.
All the time. Imagine an architecture where your entire medical history is hashed and secured on a ledger. The data itself isn't public, just the cryptographic fingerprint.
Right.
When you visit a specialist, you generate a localized smart contract that grants them temporary mathematically restricted access to decrypt specific files while permanently logging an unalterable record of that access.
Or consider the mechanics of corporate governance and blind legal bidding. You could submit complex financial bids via commit reveal schemes, guaranteeing that no central auctioneer can peek at the bids early or manipulate the timeline.
But the ultimate manifestation of this technology, the true evolution of the Hangman zero-knowledge structure, is in civic infrastructure.
Absolutely.
Think about the vulnerabilities and the constant accusations that plague centralized voting systems globally. Imagine a civic architecture where every single ballot cast is securely hashed and published to a public ledger.
A completely transparent election.
Any citizen anywhere in the world could run a node, audit the ledger, and mathematically verify the exact tally of the vote with zero margin of error.
Yet, because of the zero-knowledge cryptography we've explored today, the specific identity attached to each vote remains a perfectly kept, unbreakable secret.
Exactly. We aren't just talking about the future of digital asset ownership or gaming here. We're talking about engineering the foundation for decentralized truth.
The cryptographic primitives are functional today. The high-speed infrastructure is deployed. We are simply waiting for the application layer to catch up to the potential of the consensus layer.
It's an incredible space to watch evolve. Thanks for diving deep into the architecture with us today. We'll catch you on the next one.